estimates are based on more information than others. The degrees of freedom of an estimate is the number of independent pieces of information on which the estimate is based. For example, an estimate of the variance based on a sample size of 100 is based on more information than an estimate of the variance based on a sample size of 10. As an example, let's say that we know that the mean height of Martians is 6 and wish to estimate the variance of the heights. How we know the mean height is 6 is our secret. To estimate the variance, we randomly sample one Martian and find that its height is 8. Recall that the variance is defined as the mean squared deviation of the values from their population mean. We can compute the squared deviation of our value of 8 from the population mean of 6 to find a single squared deviation from the mean. This single squared deviation from the mean is an estimate of the mean squared deviation for all Martians. Therefore, based on the sample of 1, we would estimate that the population variance is 4. This estimate is based on a single piece of information and therefore has 1 degree of freedom. If we sampled another Martian and obtained a height of 5, then we could compute a second estimate of the variance, 5 minus 6 squared, which equals 1. We could then average our two estimates, 4 and 1, to obtain an estimate of 2.5. Since this estimate is based on 2 independent pieces of information, it has 2 degrees of freedom. These two estimates are independent because they are based on 2 independently and randomly selected Martians. The estimates would not be independent if after sampling one Martian, we decided to choose its brother as our second Martian. It is pretty rare that we know the population mean when we are estimating the variance. Instead, we have to first estimate the population mean with the sample mean. The process of estimating the mean affects our degrees of freedom. Returning to our problem of estimating the variance in Martian heights, let's assume we do not know the population mean, and therefore we have to estimate it from the sample. We have sampled 2 Martians and found that their heights are 5 and 8. Therefore, m, our estimate of the population mean, is equal to 5 plus 8 divided by 2, which equals 6.5. We can now compute 2 estimates of variance. Estimate 1 equals 8 minus 6.5 squared, which equals 2.25. And estimate 2 equals 5 minus 6.5 squared, which equals 2.25. Now for the key question. Are these 2 estimates independent? The answer is no, because each height contributed to the estimation of the population mean. Since the first Martian's height of 8 influenced the estimate of the mean, it also influenced estimate 2. If the first height had been 10, then the estimated mean would have been 7.5, and estimate 2 of the variance would have been 6.25 instead of 2.25. The important point is that the 2 estimates are not independent, and therefore we do not have 2 degrees of freedom. Another way to think about the non-independence is to consider that if you knew the mean and one of the scores, you would know the other score. For example, if value 1 is 5 and the mean is 6.5, you can compute that the total of the 2 scores is 13, and therefore that value 2 must be 8. In general, the degrees of freedom for an estimate is equal to the number of values minus the number of parameters estimated and root to the estimate in question. In the Martians example, there are 2 values, 8 and 5, and we had to estimate one parameter, the population mean mu, on the way to estimating the population variance. Therefore, the estimate of variance has 2 minus 1, or 1, degree of freedom. If we had sampled 12 Martians, then our estimate of variance would have had 11 degrees of freedom. Therefore, the degrees of freedom of an estimate of variance is equal to n minus 1, where n is the number of observations. Recall from the section on variability that the formula for estimating the variance in a sample has n minus 1 in the denominator. Specifically, the estimated variance equals the sum of the squared deviations divided by the number of observations minus 1. The denominator of this formula is the degrees of freedom.